This is a problem we did. I'm going to talk about it. In this section 3.3-2, there's some stuff that they talk about, but the really important stuff is coming up later, and you'll see how this all works together. So this is 3-2.2. And in this one, you have to go back to a previous problem, I believe. Isn't that right?
Yes.
And I have some of this information. I'm just going to put up a distribution. This is something from a prior problem. And we figured out what K was for this, the coefficient. So they give you f of x comma y, or it's found in an earlier problem, 4xy, and this is valid from 0 for x, y less than 1. I don't put the equals to or greater than, or the equal or greater than, or anything like that. And whenever you see something like this, you always assume it's 0 else. You don't even have to specify that. Follow me, class? If they tell you where it's not 0, assume it's 0 anywhere else. So after that, what do they ask?
The conditional probability density function of f of x given y.
Oh, all right. So they want f of x specified with y. I'm gonna, now, this is important to listen. Now you look at this one for a second. Are these things dependent or independent on each other? Statistically independent. And why?
They're independent because they don't, when you integrate, they don't depend on each other.
Yeah, and they're separable. I can break that into an f of x and an f of y. Can you all see this, class? As a matter of fact, and I want to be clear about this, you could say we can do the integration, but you're going to see that fx of just x is going to be 2x for x greater than 0, less than 1, and 0 else, and fy of y is going to be 2y for 0 greater than y, less than 1. We can prove that. We actually did, but it's just by a simple integration. Do you all follow me on this? I don't mean to go too fast. How many understand this? With me? Now, if that's the case, f of x and f of y, because they're separable, f of x, it doesn't depend on y. It has to be independent of y. Can you all follow me in this class? So if you look at this, by definition, this would be f of x comma y over f of y of y. You all follow me? That's what the conditional probability, remember base theorem? This base theorem would actually show that if we wanted to go ahead and work through that. I'm assuming you at least know that in the back of your mind. So if that's the case, you can just write this in. You will see that f of x will just be what I said there. So f of xy is 4xy over f of y, which is 2y, and you can see that's going to be 2x for x greater than 0, less than 1, and what I just said is just verified. Can you all follow? What's the next one? F of y given x?
Yes, sir.
Do you all see that that will be just f of y? How many see this and understand that? I'm just trying to make the case. 2, 4, 6. We're really thin today, unless a whole lot of people drop, then I have filled it in. That's all right. What's next?
Yeah, for that problem.
Got one question for you. I want you to do this with me. What would be the expected value of x, y? Now we covered it, but it's been a while. How do you always get that?
It's just a double integral, and then you multiply x and y to it.
Well, yeah, and what he said is right. If we multiply this right here by x, y, we'd have 4x squared y squared. Then we integrate dx from 0 to 1, right? dy from 0 to 1, and you're going to see it's 4, and then it'll be x cubed over 3, right? Y cubed over 3. So 4, you all follow me on this, class? So it should be 4/9. Do you agree? By looking at this, 4/9. That would be the expected value. Now, something I put up earlier, there was something called the correlation coefficient. Oh, by the way, I better do this. Where I'm going to say that this right here, unless I made an error, is going to be 4/9. Okay, that's the expected value of x, y. Now, if I look at this, what is the average value of x? First, does it depend on what? How do I get it?
It's just gonna be 4 9.
It's going to be what? The integral of f of x, right? You all follow me on this? So it's going to be x times f of x, I'll put it this way, times f of x, which is 2x dx from 0 to 1. Agreed? And what's that going to be? Well, it's what? 2 integral of x squared dx is x cubed over 3, right? So it's going to be really 2/3. Agreed? How many see that y bar is going to be 2/3 as well by symmetry, arguments of symmetry? I'm going to slow down. People are writing, but how many see? I'm just want to be clear about this. You all see this, right? All right. Now, if that is the case, there's something called the correlation coefficient that I talked about. And that was rho of x, y. This will become more important later. This is called the correlation coefficient. Do you all remember that term? It's in one of the problems I gave you, right? And this is something, do you remember what that is? It's the expected value of x times y minus x bar y bar over sigma x sigma y. How many remember that? If you don't remember it, you will. You're going to get this over and over again in the next several lectures. And that came from the covariance matrix that I'll spend a little time with in a second. But there's a reason I'm doing it for this problem. We don't even need to do sigma x and sigma y. Why is that the case? What is the expected value of x, y? 4 9s, right? What is x bar? Well, x bar is going to be 2/3, y bar is 2/3. When we multiply them, we get 4 9s minus 4 9s are 0. I don't care what sigma x. So this is 0. And by the way, the correlation coefficient for anything that's statistically independent is always 0. This is one of the points you have to remember this, because so many problems don't say the correlation coefficient is 0. They state there are 2 statistically independent random variables. That's the reason I'm kind of making a point just with the simple one. So that's, is there another part of that one? Okay. I was going to do 3-2.3. I'm going to save that one. That one is really just about getting a feel for the most likely value of something with conditional probability, but it really has to do with taking a derivative of, if I look at this, say I have f of x, y, and it is a function of x and y, with me? Then if you wanted the peak value of this, how would you always get a peak value? Now remember, y would be a constant here. What do you always do? If you have any function, f of x, and you want the maximum value, take a derivative, right, and set it equal to 0. Do you all agree? And then that value, you go back and check the value of f of x given y, with me? To make sure it is in fact a peak, not a minimum, because it could be a minimum, right? Okay. We're going to skip 3-2.3. Now this one is kind of one, they don't, Tom Penny in his slides didn't talk about doing this one, but I think it's useful to do this. This is going to be 4-2.4. Pay attention, or 3-2.4. I want you to pay attention to this one, because there's things in here that will be important to see. Could you read that one for me?
A random signal x can be observed only in the presence of independent additive noise n.
So x is going to be a signal, right? And so then there's noise. It's just random. Is that right? Random noise.
It doesn't really say.
All right, keep going.
The observed quantity is y equals x plus n.
All right, so this is really, you might say there's a sender and a receiver. So the way I like to think about these problems, you got a sender, and then you have a channel, and the channel is going to have additive noise. And over here, this is the receiver. You can call this x, call this n, and the receiver y is going to be the noise plus x. So it's noise in the presence of signal. I think it's obvious what I'm saying, right? So what does he want here?
This is the joint probability density function of x and y is k.
Okay, hold on. Now he gives you f of x, y.
Yeah.
By the way, most of the time, they'll give the density function for x as a noise function, with me? And then if you know, I want you to listen to this. So, don't worry about that, but if you have, say, f noise, this would be a voltage, by the way, of the noise, would be equal to like 1 over the square root of 2 pi here, and call it sigma of the noise, and then exp to the minus, and this would be the noise voltage squared over 2 sigma noise squared. You all recognize that as Gaussian, right? If you take a look at this, if I say, I'm doing this for a very important reason. If I say y equals noise plus x, can you all see that noise would be equal to y minus x? Just take a moment. Do you all agree? Now remember, n is a voltage here. They're all voltage. Think of it that way. They have to be the same units, right? Okay. If that's the case, can you see right here, that's important, my f of n, and this would be y minus x, because that's what the noise is, would be equal to 1 over the square root of 2 pi, sigma noise, hopefully they give that, I'm assuming it's zero mean noise, which is almost always the case, exp minus, and this would be y minus x squared over 2 sigma noise squared. Can you all see that? Now you have an f of x, y, right? Follow me? F of x, y, right there, because of the noise voltage. This problem doesn't say that precisely, but anyway, he's going to give you the f of x, y, which is not this, but I want you to just see this. If you have something where they say the noise is Gaussian with a certain standard deviation, zero mean, then you can get f of x, y the way I showed you. If that is this is a standard communication channel. They got a sender, they got noise added before it gets to the receiver, and they want to know, obviously, this is pertinent to the previous problem that I didn't do, but it's important to see that. But go ahead, they give you this, which is okay.
It equals k exp to the minus, and then in parentheses, it's x squared plus y squared plus 4xy.
Over.
That's just it.
Oh, okay.
And then that's for all x and y.
Now, what does he ask for?
Find a general expression for the best estimate of x as a function of the observation capital Y equals lowercase.
I want you to just see one thing about this. Whenever you have this function, and they say best estimate, they're really talking about the peak value of this. Y'all follow me on this? Best estimate of x, y with any condition? Does he have any condition? In other words, the peak value of f of x comma y. But he has to have something else. What is it?
As the function of the observation capital Y equals lowercase y.
All right, so what he's really saying is we're going to have a received signal that we know. Now we want the best estimate of this f of x, y. Can you all follow me on this, class? So now when you take a look at this right here, we've got a received signal that we know, given. So we take a derivative of this, f of x comma y, with respect to x, because y is stated. We observed it, we know it. We don't know x, with me? And they want the best estimate of x, right? The sense, the signals. So what is this going to be? Now take a look at this. Here's why k doesn't matter. K is going to be a constant. I don't care what it is. But when I take a derivative of that whole thing with respect to x, can you all see this? I'm going to get minus, now take a look at this, derivative of this inside that exponential, because that's the thing that's going to come out, right? It's going to be what? Minus 2x, right? So minus 2x. The derivative of y squared, we know y, with respect to x is 0, correct? then the derivative of that with respect to x is going to be 4y. Do you agree? So 2x, and it's going to be plus 4y. Remember, I took the minus sign out there. And then it would be times that whole exponential too. It doesn't matter. You'll see why in a second. X squared plus y squared plus 4xy. How do I find, if I want the best estimate, I have to set this equal to 0, don't I? I'm going to stop for a second. I want you to just think about it. Last night I was doing this, I'm like, how would I teach this without just whipping through? I'm going to stop and ask you to think. What solves this?
K equals 0.
Yeah, but K can't be 0 if it's a statistic, if that is a distribution. I mean, it has to be something, if you integrate over all x, y, you get 1, right? K is going to have a value. I don't care what it is right now, it doesn't matter. But what would it be? Can you see that this thing right here, the only way it goes to 0 is for x to go to infinity or y go to infinity, with me? So don't worry about that. But what about this? If that 0 isn't 0, that's the coefficient of that exponential. So the maximum value of that is going to be when minus 2x minus 2 or minus 4y equals 0, or really what? Here it would be x is equal to minus 2y. Take a look and see if you can follow me on that. Just take minus 4y to the other side, you get plus 4y divided by minus 2, you get minus 2y. Agree? Remember, y is seen, so the most likely value of the sender would be the thing that solves that for x. And does he give you a specific on this one? I think it's wise to bring that out.
He does. That's in the second part.
Okay, and you can take a look. This is 3-2.4. So anyway, really the thing is, if x is equal to minus 2y, you're going to get the maximum value of that function. If you have y, that would be the most likely value for x. With me? A lot of times they worry about, is that right? I'm sure it is, but and the next part is what?
For when y equals 3.
All right, this is just simple, right? Y equals 3, x is minus 6. Is that what we have?
Yes.
So this is the way, it's a very simple way of a problem like this being done. I'm going to make another statement. If you look over here, and if we had the noise, remember this is f of yx, right? And we want, remember, we're going to know y. How would you calculate the most likely value of x? It's the same, this is the same kind of distribution as that, right? This is an f of xy, this is an f of xy. With me? It's a function of both x and y, right? So what do I have to do? Take a derivative of this with respect to x, because y is stated, and set it equal to 0. Now, the derivative of this one isn't bad, right? Just take a look at this. We're going to get this coefficient. Doesn't matter, because it's going to be set equal to 0, right? Then you're going to take a derivative of this. Well, you're going to get the 1 over 2 sigma n squared coming out. Then you're going to get a minus sign, right? Then you're going to get a 2y minus x, right? And the derivative of this with respect to, in other words, here's what's really going to be the root of this one. If you look at this, and I'm going to use this function for f of x, y, not that function. Then when I take this and I take a derivative, and I'll call it f of y minus x here with respect to x and set it equal to 0. Well, that derivative, obviously, is going to have all the usual suspects, the 1 over square root of 2 pi sigma, the noise, and then it's going to have that. But when you take the derivative of this, you're going to get minus 2 quantity y minus x, but a derivative of this with respect to x, the inner part makes that plus, and then you're gonna have that exponential that you don't care about really, all that stuff, equal to 0. This goes away, right? You can forget the 2, forget the exponential, so it's y equals x. Can you see that, class? With me? What I'm really making a point about is this distribution here could be replaced by that one, and we do the same thing, take a derivative set equals 0, and that would be the most likely value of the descent signal. Now the interesting thing on this one, because it's just going to be, I didn't even show you that, it's going to be y minus x is 0. It's when y is equal to x, or the sending signal, the most likely value of the signal received, sending signal, if the received signal is y. Follow me? Because that noise is 0 mean, it's Gaussian distributed. That was my point on this one, to try to make you aware of that. Whenever you get these Gaussian distributions added, and they want the most likely value, that would be it. Now, if it's a conditional probability, it's a little different. But we'll get to that. All right. Did he have another part to that one?
That was it.
All right. Hang on. All right. This one I want to do from Denny's notes, and we're going to calculate. Yeah.
Sorry, maybe I missed this, but so what exactly? And maybe you were just saying it, but what does each of these separately tell us? What's the difference between?
Well, the real difference is right here. This one does not have a Gaussian distributed f of x, y. This is something we've got. He just gave it. All right, and the Gaussian distribution is a well-known distribution.
So what's the usefulness in either one?
Well, the Gaussian is realistic.
Yeah,
No,
so that's
Gaussian.
just, if they
This
can
is
do
just
that.
something to get you familiar with the method. You have to take a derivative of f of x comma y and set it equal to 0 if you want the peak value of that joint distribution function. That's the idea on that one. Remember, y is known, x is not, so you have to take a derivative with respect to the unknown, set it equal to 0, and see what the peak value of f of xy is, and that's the most likely value of x, in fact. Even though it doesn't say it is a value, it's the most likely. Okay. Did you have a question? Let me go on to the next idea. And I'm going to make a couple of points. Okay, I really want to underscore this because I think it's important to say. Any news on campus these days? Besides Hugh Freeze is playing a lot of golf because it's his off time. When I saw that, I'm thinking, you guys really have nothing to report, do you? You know how much golf Nick Saban played? Tommy Tucker. They need to talk about something. Why not golf? All right. So now we're going to talk about these non-statistically independent cases where there is a correlation coefficient. And I have to say one thing. So this is going to be something you'll see over and over again, probably in your upper level courses when you have communications. You haven't had comm, I don't believe. When you have communications and some of the other courses, you'll see this term. You've heard of variance mean already, right? It's covariance. Covariance. I'm just going to put it the way it is. It's usually COV is the symbol, covariance. And a covariance of x comma y is defined as it's the expected value of x minus x bar times y minus y bar. So if you look at that, this is really by definition a double integral, and it would be x minus x bar, y minus y bar, and here then you're going to have f of x comma y, dx dy, and the limits here would be something that correlates to the definition of when f of x, y is non-zero. That's the only thing I'm showing you, okay? Now, if you look at that, that doesn't mean a whole lot, but here's some things to get. If you have the covariance, it's not brought out in the book, of x comma x, all right, x minus x bar times x minus x bar, follow me? That's x minus x bar squared, right? That's the definition of the variance, right? So this is simply the variance of x. With me? I want to make sure you see this. If they are statistically independent, okay? Then if you look at this, the covariance of x comma y, if these are statistically independent, is 0 if they're statistically independent. It will be that, all right? If they're statistically independent, you know how to prove that, by the way? Why don't you take a look at this? If they're statistically independent, just as a side note. So if we have the expected value of x minus x bar times y minus y bar, this is statistically independent. Take a look at what this is. Isn't it the expected value of x minus x bar times y minus y bar, right? Y'all agree with that, by the way? Think about this. X bar, y bar constants, right? So if I look at this, and this is additive, what's the expected value of this? Well, it would be x bar minus x bar, and this would be y bar minus y bar. Think about it. If you had the expected value of x minus the average value of x, it's really the average value of x minus the average value of x. Do y'all see that? So it's 0. Y'all with me? So if they're statistically independent, it's 0. Has to be, by the way. Y'all follow me on this? That's important. And we'll get to a little bit more about this, but when you look at the correlation coefficient, rho of x, y, and by the way, always put down, he doesn't always do it in the solutions. In the book, I think he does. Whenever you talk about a correlation coefficient, you have to indicate between what variables. So what this is really the covariance of x comma y over sigma x, sigma y. He doesn't really spend much time showing you COV. He doesn't. He'll use VAR of x, but he doesn't use COV. COV is very, very common in terms of its usage. It indicates covariance, and that's important. Now the truth is, if you look at this and you expand it, you expand covariance and then you go ahead and move out. But this is going to be the expected value of x times y minus x bar y bar. We could prove that. I don't think we have to here, over sigma x, sigma y. This is important too. Now remember, if they're statistically independent, then this is equal to that, and it's 0, always 0. Okay. Now we're going to do one. We're going to calculate the correlation coefficient. But this is a weird distribution, and I want to make sure you see. Let me erase that and put it here. This is in Dr. Denny's notes. I think I ask you guys this almost every day, but is it going to rain later today or not? I didn't know. Yesterday it said it wasn't, but anybody know today?
Maybe like 3.
Pardon me? 3 o'clock?
Maybe small scattered thunderstorm chance.
So for this problem, now this is a kind of a weird one. It's f of x, y. I've got some questions. So it says f of x comma y is equal to x plus y for 0 greater than x comma y less than 1 and 0 else. With me? First, by inspection, is it or isn't it statistically independent? And why? CJ, why?
Because they're inseparable.
You can't get just an f of x and just an f of y. Follow me? And if you go ahead and integrate it, you're going to see f of x times f of y is not f of xy. Follow me, class? So, now what we're going to do is something where what he wants is, he wants this, the correlation coefficient. So now I want rho of xy. Technically, it's what? The expected, but we can do it with covariance, but this is easy. Of x times y minus x bar, y bar, over sigma x, sigma y, right? Agreed? Let's go ahead. If I ask you to do this in the next 15 minutes for 10 points, how would you go about doing it? I'm trying to give you at least some thought where you're going to force yourself to think through this one. Well, let's try this. How would I get x bar? Anybody? What do I need to get x bar? F of x, right? So how do I get the logical question? How do I get fx of just x, and while I'm at it, fy of just y? I need these, don't I? If I'm going to get mean values, that's what I need. Follow? And remember, these are not statistically independent, so this is going to be an interesting one. With me, class? How do you get them?
F of xy over fy or the f of x.
There might be probably a better way. This is not a conditional probability problem. Remember, if you have f of y given x, then it's f of xy over, then it would be over f of x. Follow me? We don't have conditional probability. If we don't have conditional probability, the way to get this is by integrating that f of x comma y. And in this case, if I want f of x dy, right? So this one would be the integral from 0 to 1 of f of xy, x plus y, right? And it would be dy. Now first, do you agree with that? I'm just trying to get this information. We'll use arguments of symmetry for the other half, but. So if I look at this, I get x, really, when I integrate dy times x, I get y, from 0 to 1 is just 1, so it's x is the first term. And then when I integrate y dy, I get y squared over 2, evaluated from 0 to 1 is a half, right? And this would be for x greater than 0, less than 1, and 0 otherwise. Y'all agree with that? What about, I bet you guys can say this, based on arguments of symmetry, what do you think this is?
1 half plus x.
Y plus 1 half, right? From 0 greater than y, less than 1, and 0 else. Do you agree? It's pretty obvious if you look at this, right? The next step is, now how do I get x bar? That's the expected value, right? That's the integral from 0 to 1 of f of x, right? Which is times x. So it's going to be x times x plus 1 half dx. First, I'm going to make sure everybody sees this before. You understand it? I just take the very definition. The expected value of x, or x bar, is simply that value x times the density function f of x integrated. You all agree? Does everyone? All right, what is that going to be? Well, I got x squared integrated dx. That's going to be x cubed over 3 from 0 to 1. Is going to be 1/3 here, right? And then I have x, 1 half x dx, or x squared over 2 divided by 2, x squared over 4 from 0 to 1, or plus 1 to 4. Do you agree? And I don't care how you do this. So it's really going to be 4 plus 3 over 12, or 7/12. Export. Let me just see. Do you all agree with this? And I like this. Arguments of symmetry. You guys are very smart. What is y bar gonna be?
That's 12.
You all see it's 7, give me 7 12. Okay. We got that done. Right? Now, after that, I guess we can do expected value of x times y next. I'm trying to do this in an order that's simple. Yeah, let's do the expected value of x times y. Why don't you help me with this one? So the expected value of x times y, it's going to be a double integral, right? And here it's going to be from 0 to 1, 0 to 1, x times y times x plus y, dx dy. First, gotta make sure everybody agrees with that, right? What's this going to be? Let's see. Now we'll do the dx integral. I'll break it down into 2 integrals first. 0 to 1, 0 to 1. So I'm going to have x squared times y dx x dy plus double integral of x y squared dx dy 0 to 1, 0 to 1. And why I'm doing that, can you all see that this and this will be equal to each other? I want you to make sure this has to equal this, doesn't it? By arguments of symmetry. I want to make sure. Y'all agree with that? Take a look at this. We got x squared dx y dy. Over here we have y squared dy x dx. Switch x for y and you get the same thing, right? So what I'm going to do is just get one of these and I'll multiply by 2. So it's going to be 2 times, and then when I do this integral, look, I'm going to take x squared dx, I get x cubed over 3, right? From 0 to 1 is 1/3. And then I take y dy, or y squared over 2 from 0 to 1 is going to be times 1/2, right? And I multiply it by 2 because there's 2 exactly identical integrals in terms of the results. Agreed? And you can see that's 1/3. Agreed with that? We're not quite done. You can see there's a lot of little trivial things you might say associated with solving this. So now somebody tell me, how do I get sigma x? Or sigma x squared, the variance? Well, y'all know that sigma x squared is equal to what? X squared bar minus the mean value of x squared, right? Do we have the mean value of x?
Yes.
We can square that. Do we have x squared? How do we get x squared? Now, these are one of these things that some people will go and see a problem. I'm not confident. I don't have to use f of x, y, you know. Remember, what is this by definition? It's the expected value of x squared, right? Independent of y. Do y'all agree with this? So how do I get it? Well, x squared bar would be equal to what? Integral from 0 to 1 of x squared times f of x. What is f of x? X times x plus 1/2 dx, right? I might add, we could use arguments of symmetry to get sigma y squared based on this, but let's go ahead we could get y squared bar. What is that going to be? Well, I got x squared times x, that's x cubed dx, right? Or x to the 4th over 4 from 0 to 1. First, y'all agree with that. So that's 1/4 is the first term. And now I have simply x squared times 1/2 dx, or it'd be x cubed over 3 divided by 2 from 0 to 1. Or that's going to be 1/6. First, do you agree with that? By the way, if you ever feel unsure about this, just use your calculators. It'll save you points. Don't make dumb mistakes. And what's that going to be? Well, I don't care how you do this. Let's common denominator.
Be 5/12.
So that's going to be 3 plus 2 or 5/12, is that right?
That's what I got.
5/12, right? Okay, we're not done yet. Now what's this gonna be? Well, that would be 5/12, what's x bar? Minus 7/12 squared, right? And by the way, do you agree that would be sigma y squared? So I'll put this as sigma y squared as well. Now if I look at this, I'm just gonna put it over here. I'm gonna get sigma y equals sigma x. And because of that, just notice this, because of this, down here, this is really sigma x squared right there. Can you all see that? What I'm really saying is, we've got this, since sigma x equals sigma y, this is sigma x squared or sigma y squared, right? So what is this gonna be? Right, the expected value of xy is 1/3, right? Minus x bar, y bar, which is gonna be 7/12 squared, divided by, boy. So what do we got here? 5 times 12 minus 7 over 144, boy. Take that from anyone. That's 49, 144. Yeesh. I don't want to mess with that one. I can tell you what I got somewhere. I think it's going to be minus 1/11. But anybody?
11 over 144.
Over what? 134?
144. That's what I thought.
144?
Let's just see.
Hold it.
Let's
Oh,
just
that's
work
right.
there.
Isn't this, all right, so if I'm 60, isn't that minus 111?
Yeah,
Yeah.
that was a variance, I think.
Minus 111. All right, now that's a negative correlation coefficient, right? I want to just mention this again. I did it last class, which is quite a while ago. If you plotted, it's a negative correlation coefficient between y and x. So if you plotted on this axis y and on this axis x, and you just plotted this, it's a negative correlation, so the overall slope would do this. There might be dots here and here, but you would see the general trend would be downward. Can you all see this? It wouldn't be that pronounced, it's minus 111, it's a gradual slope. You with me, class? And by the way, if you look at those slides, has anybody taken a look at the slides and saw the correlation coefficient is 0? It's just random distributed of dots. Correlation coefficient of positive, it's like there's a positive line and the dots are within a certain standard deviation of that, more or less the relationship between x and y. Then negative is going down, but this is important. I'll tell you where it's really important is with radar. When you're doing tracking algorithms, and you're wanting to estimate, best estimate where the plane or object is, the target. When it's moving, there's all sorts of things that make it a statistically varying bit of information you're going to get back. Now, do you know what a Kalman filter is? Where'd you hear about that, Bob?
My systems class.
Our Kalman filters predict the next logical point in where something's going to be. Well, if you use a Kalman filter and you look at the past history of what's been going on, you get a much better estimate if you know the correlation coefficient of where it's going to be next. And that's so important with radar tracking. You have to guess where it's going to be with a high order of precision so you can move your tracking radar to that point and see if in fact it is there. Okay. Got that. And in fact, that's how you would do this problem. But it's a really a good problem. Now the next part I'm going to show you, this is in section 4. We're going right into there because this is important. I want to tell you, this gets a little tricky. I try to always tell you ahead of time that something's coming up that's going to be more challenging, or things about this, you're not going to see certain things unless you pay attention here, or not very easily. In Dr. Denny's slides, he goes through this and he proves this. It's kind of a lengthy proof. How this works is probably going to be needed here. But what we're going to do is this. We're going to assume we have two random variables, x and y. Okay. And these random variables, this may be given, it may not be given. Okay. Now, if we take a look at a third random variable, z, that is equal to ax plus by. Now, we can extend this for as many random variables as we want. Y'all with me? This is a function of both x and y, but it's not just x and y. It's something where there's a coefficient. I want to tell you something else. In general, if z is of f of x comma y, it gets much more complicated, but I want you to just understand this. Now, a and b are constants. So for this one, remember, we know that correlation, and I'm going to just go through this sort of the way he does. First thing you always need when you have this kind of a problem, you need to at least, almost always you need this, I should say this. What I'm looking for is the standard deviation, or I'm sorry, the variance of z, you all with me? And I may be looking for the correlation coefficient between z and y, for instance, or z and x. Do y'all follow me, class? We don't know yet, but I want you to follow me. We want that for sure. So the first thing you have to get is the expected value of z. Well, how do you always get the expected value of anything? Let me go further. How about if I just take the expected value of what z is defined as ax bar, or ax, pardon me, right, plus b times y. I think you can say that these two, it's the linear system right here. We can simply say it's expected value of a times x, right? The expected value of x plus b. So this is really a x bar plus b y bar. Straightforward enough? Whatever it is. And I didn't put the density function, but we can get that. That's the expected value of x and y. Now, what is to get this, we're going to have to get the expected value of z squared. This is something to pay attention to. So what is the expected value of z squared? Well, it would be the expected value of ax plus by squared. I'm just putting down the very definition of z. Agreed, class? Now square it out, what do you get? It's equal to the expected value of a squared x squared plus b times b squared y squared plus 2ab x bar, sorry, x times y, not x bar, x times y. The only thing I did is multiply that out. Do you agree? Remember, a and b can be anything. And that would be equal to a squared times the expected value of x squared plus b squared, expected value of y squared plus 2ab, and this is the expected value of x times y, and that would be simply, I call it z squared bar. Agree with that? I'm just putting it out there. I'm going to expand this a little more. I'm going to only do this one time, and I'm trying to make sure you see the logic. It's straightforward, just a little nerve-wracking because there's so many steps to this. Okay, now if you take a look at this, z squared bar, well this, it would be a squared. Now notice this, because that's the variance, I'm sorry, that's the, that's x squared bar, that's really sigma x squared plus x bar squared here. Can you see that by taking the expected value of x squared, sigma x squared, plus the mean value squared, right? Keep going on this one. Plus b squared, and this would be sigma y squared, plus, and here it's going to be equal to y bar squared. And then this one, now this is important, because if you look at this, the correlation coefficient between x and y is equal to the expected value of x times y minus x bar times y bar over sigma x sigma y. I can say the expected value of xy is equal to rho xy times sigma x sigma y, and then it would be plus x bar y bar. I'm just solving for the expected value of x. But y'all agree with this right here? I want to make sure that it's in the back. Can you see it? You okay? Can you see it? I'm just trying to solve this because that's what I have here. So this is going to be plus 2a times b, and that is going to be this times, you're going to have to forgive me on this. I'm going to go to the next board. It's going to be rho of xy times sigma x sigma y, and here plus x bar y bar. That's the whole lot of information. Are you with me? I'm just putting it down here. Now you look at this, one thing you're going to see is all through here is on this side nothing but x, y, and the correlation coefficient information. Come over here, I got z squared, oh, and that is equal to, and that's really equal to sigma z squared minus z bar squared. Can y'all follow me to that? Remember, that's what I'm after. You with me? Gets a little irritating, you can see. When I do this right here, did I find z bar? Yeah. This is, I didn't put it down, that is, I shouldn't say. This is the expected value of z. This is z bar, right? Now, see, that's what goes here. And so z bar there, take a look at this. I'm going to take minus z bar to the other side, the square of it. This is going to be plus that squared. So then I get a x plus b y squared. That's a whole lot. It's a mess. I mean, I was messing with this last night. You're going to see a whole lot of things can be grouped and canceled. I'm going to just make a mention of one. Take a look at sigma x squared. Right? You look at that, it appears here and only here, right? You got a sigma x squared. Next thing you see is it's going to be equal to sigma y squared. I don't see any other sigma y squared but this one. Follow me? So you got b squared sigma y. Those two break out. Now when you get x bar right there, and take a look at squared, it'll appear here, and it'll appear here. Can you see that when you square it? You get y bar squared here, it'll appear here and here. Whole lot of just grouping and rearranging, and you get all this stuff. And then, this is one of those things. Here's what happens at the end of the day, and I want you to understand. We can mess with that if you want, but I need to erase this because I defined it in terms of sigma z squared to get this. At the end of the day, and this is the thing you write down, when we group everything, you're going to find this. You get sigma of z squared, that's the variance of this, is really sigma of quantity ax plus by squared. Remember, that is the definition of z, right? That's what we defined. Z is a times x plus b times y, right? X and y are right. And what that is equal to is going to be a squared sigma x squared plus, this is after everything, b squared sigma y squared. Then it's going to be plus, you'll be able to get this in no time, but it's going to be 2a times b, and here it's single, it's sigma x, sigma y, but it's times rho of xy. And I want to tell you, after you do all this stuff and condense it down, after everything's said and done, that's what you get. And that's important. And this one you commit to memory. When you see that I do this on anything, it means you've got to know it. It's not, this is something you got to know. It's like F equals MA or B equals I times R. You have to know these things. All right, now, that said, we got to do a problem. Can you do 3-4.1? I know sometimes doing problems takes a lot of class time, but applying these things is the only way to see, there's some tricks. I want to work through, give me enough time to do 2 problems. I won't hold you too long, but I want to get through these things. There's some real tricks in this stuff. There may be other ways to write that, but that's, in my opinion, easiest and the one to keep in mind. Okay, so this is 3-4.1. Can you read that?
two random variables have 0 mean and variances of 16 and 36. Their correlation coefficient is 0.5.
36?
Yes, 16
Okay.
and 36.
And the means X bar, Y bar equals 0. Go ahead.
And then the correlation coefficient is 0.5.
Okay, go ahead.
Find the variance of their sum.
All right, so this is straightforward. Z is equal to X plus Y, right? The only thing we're gonna do is apply the formula I got over there, and it is a no-brainer at this point. So here, he wants the variance of Z. In other words, he wants sigma squared of Z. So it's A, can you see here, A and B are both 1. That's the coefficient of X and Y. Can everybody see this? Right, I gotta make sure on this one. So this is gonna be A squared times sigma X squared. So it's really sigma X squared plus B squared. B is 1 times sigma Y squared plus 2 times sigma X, sigma Y, right? And then it's going to be times the correlation coefficient of XY. That's the, A and B are 1, so I didn't have to put them down there. But you see how that formula and this formula agree. So he gives you sigma X squared as 16 plus sigma Y squared as 36 plus 2, sigma X is going to be 4 and sigma Y is 6 and rho of XY is 1/2. So I got 16 plus 36 plus 24, right? So if I look at that, 36 and 24 is going to be 60, so it's 76. And you've got the solutions there, but I'm pretty sure that's right. Do y'all follow me in this class? What's the next part?
Find the variance of their difference. Of their difference.
Okay, almost the same thing. But now what he's going to do is say Z is equal to, I'm going to put it as Y minus X. It really doesn't matter. Now, on this one, there's one slight difference, right? For this one, if I look at this, A is equal to -1 and B is equal to 1. I want you to just take a look at this in the first degree or disagree. Do you agree with this? This is just the coefficients related to X and Y. One of them is negative, one of them is positive. Agree? So what happens here? For this one, part B, now we get sigma squared of Z equals to, well, it's A, and A is -1. And this should be, the way it should be done is A squared, so that's still going to be 1 times sigma X squared plus B squared, it's 1 again, or sigma Y squared, but then it's going to be minus, because here A is -1, B is 1, so this is going to be -2, all right? So it's -2, and then sigma X, sigma Y, and the correlation coefficient is 1/2. So that means I got what? 16 plus 36 minus 2, well actually, minus just sigma X, sigma Y, or minus 24, right? And what is that going to be? That's 12 and 16, is that 28 class? Which, 12, yeah, 16 is 28. Looks like 28 for sigma Z squared. Is that right, Elijah? Part B of 3-4.1. I think it is, but I don't remember.
That's right.
Okay, now what's the third part? Where is the third part?
Repeat A and B if the correlation coefficient is -0.5.
Let me ask you this, can you handle that one? The only thing you're doing is changing an X row of XY, that's it, but it's get you familiar with it. I want to do the next problem, let's see if I can run through this. So this is going to be 3, this is an important one. 3, it's a trick, I think it's this one. Let me do it right here, give me 1 second. 3-4.2.
Two statistically independent random variables, X and Y.
Alright, I'm gonna put this statistically independent means row x, y equals 0. This is so important. That's where you get that information on the value of row x, y. Got it? Go ahead.
Sigma x squared equals 9. And sigma y squared equals 25.
Go ahead.
Two new random variables are defined by u equals 3x plus 4y and b equals 5x minus 2y. It says find the variances of u and v.
Now. So they want the variance of u and the variance of v. This isn't bad right here. Are you with me? All right, let's do the top one first. How do I get this? Now, from this one for you, can you all see here that A would be 3 and B would be 4? First, I gotta make sure that's for this, for you. Take a look over there. Y'all see it? Well, I didn't put it down here, but if you have Z, doesn't matter, is equal to AX plus BY, then that results. Follow me? A is the coefficient of the first variable, B is the coefficient of the second variable, and there is a row XY that is known. Now, because there's this statistically independent, row XY is 0. Can you all see this? This part is simple. What is sigma u squared going to be? Well, technically it's what? A squared, right? Sigma x squared plus b squared, sigma y squared, plus 2a times b, sigma x, sigma y times row of xy. First, you see, the only thing I'm doing is taking that definition and rewriting it. Now put the values in. A is 3, right? By the way, what is row of xy?
0.
0, so we get rid of all that. Boy, that's a lot. I like that. So here I take a and square it, I get 9, times sigma, this is a big number. I get 9 times 9, it looks like, right? Sigma x is 9. I hope I got that right. Sigma x squared is 9. And b is 4, so plus 4 squared is 16, times sigma y is 25. 81. I think this is 481, but somebody better check me on that.
Yeah, it is 480.
All right, how about sigma v? You guys can do this as fast as me. For this one, A is 5, right? 5 squared is 25. Sigma x is going to be 9, right? And then it's going to be plus b squared, or plus 4. Sigma y is 25. 325, I think I remembered that. You tell me if I'm right. I think I remembered that one.
That's right. He's right.
Okay, 325. Now they say one thing, and this is the thing you pay attention. This is the trick I'm going to show you. What do they say?
Find the correlation coefficient of u and v.
All right, so they want row of u, v. Okay. Here's u, here's v. How would you get that? Now I'm asking, just think about it before I give you the answer. Well, I don't have a variable that has u and v in it, right? How could I get one? Well, I could say u plus v, right, is equal to z. Follow me on this one? And then I could say, if I've got that, I could say sigma z squared, y'all follow me? If you did this, you would expand that, but here is the trick. If I take a look at this, if I could get a function z that is only a function of x or y, my life would be easy, and I want you to see this. This is a real important little trick. I want to do it right here. So I have u is equal to 3x plus 4y. I'm going to rewrite it. And I have v is equal to 5x minus 2y. Everybody agree? What if I create a variable, and he does this in the solutions, it doesn't have to be this one, there could be another one related to x. Suppose I take this and said, it's equal to u plus 2 times v. That's my new variable. You always, I've got to have a variable that has u and v in it, or I can't get the correlation coefficient. That's the idea. Now, what do you see happening here? I have z is equal to u, 3x plus 2 times v. Can you see the y's go out? So I'm going to have 3x plus 4y, and then I'm going to have plus 10x minus 4y, or z itself is simply 13x squared, or 13x, pardon, 13x. Can you see this? Take a look. With me? Now, over here, I say sigma squared of z is equal to sigma squared of here, it's going to be u plus 2v. All with me on this? What do you see right here? Well, sigma squared of z is really going to be what? Take a look at this. If I have sigma squared of z, that's really going to be what? Can you all see that? Here's what I mean. If you look at this, what's the mean value of z? 13 times the mean value of x. Y'all with me? What's the value of z squared, right? It's going to be 13 times the value of x squared, right? The mean value of x squared, or x squared bar, correct, class? That 13 is a coefficient that comes out in front of that. You don't square it. So if I do this, this is true. Do you agree with that? Do we have sigma x squared? Yeah. So, but we've got to get this. So on this side, you can put it 13, and what is sigma x? 9, right? We want this correlation coefficient, so what is this equal to? Remember, now when I look at this, z is equal to u plus 2v for this one. The coefficient a is 1 and b is 2. Take a look at that. That's the mathematical equation. We want the correlation between u, or correlation coefficient between u and v. Follow me, class? This is an important point. I know it's at the end of class, but just let me finish this. Okay, now we apply this, and we get it's equal to a squared times sigma x, and sigma x is 9, right? Plus b squared, b is 2, or plus 4, times sigma y. This is big. He chose some big numbers. Plus 2 times a is 1, times b is 2, so it's really 4. And then sigma x is 3. Sigma y is 5 times rho, and this would be of uv. Now that's what we want. Can y'all follow me on this? So here, we want rho of uv. I know we've been going at this one you got, your class starts at the bottom of the hour, right? At 11:30, it's 11:08. We're gonna get this. I just want to finish this. So here I need rho of UV. So I've got this, and I take 13, I need your help on this, 9, that's this. I gotta take all that crap and take it to this side, minus 9, right? Then I take 4 times 25 is 100, minus 100. Now I've got all that on the other side, and I have to divide that by 4 times 3 is 12 times 5. I'm gonna put down 12 times 5, that's 60. And that should be rho of UV. This is something, let's see. So that's 12 times 9, minus 100, that's negative. Minus 4 over 60. So what do you get for this one? Is that minus 4 over 60?
It's 2/15.
What is it?
2/15. That 12 times 9 is 13 times
So it's, say it again,
9. 2/15.
negative.
I didn't do it.
Well, hold on. Isn't this
It's 13.
13 makes it 12 times 9, right? 13 times 9 minus 9, 12 times 9.
Which is
Was
108.
What?
13 times 9 is 117.
Minus 9.
Yeah, which is 108, and then there's an
Oh,
8.
yeah, you're right. And what do you get here?
2/15.
2/15. Is that the answer?
You got negative 0.1644. But I got 2/15 in my calculation.
I think that might be wrong. Did I write something in there?
No.
You check on this one. Unless I did something wrong here, I think I didn't, but that's how you would get it. You with me? You better check that one, that answer, but this is the trick. Right here, the whole trick is this. Create a variable that is only a function of either x or y. Because then you can get 13, you should have 13 times sigma x squared on one side,
Yes, that on the.
or sigma z squared, right?